This is my Calculus 1 course. Today we're going to introduce a new topic called differentiability, and we're also going to review the domain and range of functions, and also we're going to review interval notation. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. It's been a while since we studied the domain of a function. This is a very, very important concept for upper mathematics. We learned this in my intermediate algebra course, but we do have to review for the calculus curriculum. This calculus course and every other calculus course requires a knowledge of domain. So the domain of a function is all of the inputs of the function that are able to produce outputs. So for example, you might have a function f of x is equal to 1 over x. X equals 0 is not in the domain of the function, because if you plug in 0 into the function, you get 1 over 0. So if you place this input into the function, you don't get an output. There is no output because 1 over 0 is not an output. So x equals 0 is not in the domain. But every other number is in the domain. Every other real number is in the domain, because if you plug in any other number, you get a corresponding output. So again, the domain is all of the inputs of a function, typically called x values, that are able to produce outputs, which we typically call y values. The range of a function is all of the outputs of a function that are able to be produced from the inputs in the domain of the function. So an analogy that I give in my intermediate algebra course is playing video games or driving cars. All of the buttons you can push on your controller that will produce some change on the computer screen are the domain of the function. So all the buttons on the controller that actually do something are the domain of the function. Everything that your man does on the screen as a result of pushing those buttons is the range of the function. And the function itself would be the console. Maybe you have an Xbox or a PlayStation or whatever. Now, driving a car is another example of this. Every way that you can turn the steering wheel, that's the domain of the function. Everything that the car does as a result of you turning the steering wheel is the range of the function. It's all the things that the car can possibly do as a result of you turning the steering wheel. And the function itself would be the axles and the joints and everything together that makes the car respond to your turning the wheel. So these are some examples demonstrating the general idea of the domain and range of functions. Now, it's important to understand that imaginary numbers are not allowed to be inputs or outputs of most functions. So we're not going to consider those as inputs or outputs. So let's do some practice problems. It says here the graphs of functions are given. Use these graphs to write the domain and range of each function in words, set notation, and interval notation. Now, at the beginning of the class, we said that we're going to review interval notation. And we're focusing on interval notation because that is the preferred notation that mathematicians use when they get into upper courses, because it's just easier to write. We are going to review set notation also, because it's a way for you to it's a way to help you understand interval notation, and set notation is often used also, so it's important for you to be somewhat familiar with that. So let's do a practice problem here. We have a function that's represented by this graph. Remember, there's a lot of different ways to represent functions. You can represent a function with an equation, with a graph, with a table. But here we have a function represented with a graph. So what is the domain? What is the domain of this function? Well, the domain of the function is the x values of all the points. See these purple points? Whatever points are on that graph, the x values are the domain of the function. So we need to describe all of the possible x values that you can plug into that function. So the domain is all real numbers, because remember we can't have imaginary numbers as inputs of a function. The domain is all real numbers between 1, 2, 3, 4, 5, 6, between -6 and 1, 2, 3, 4, 5, 6, 7. So all real numbers between -6 and 7. But this does not include the x values at the endpoints. So we have to modify this statement. We have to put a comma here, and we have to say inclusive. I know that's kind of inconvenient to have to write that, but that's the way we indicate that the x values at the endpoints are also part of the domain. Now, if these points were actually hollow, if they were hollow dots, then we would not say inclusive. Now, in set notation, we write a brace. That's called a brace. Then we write an x, because these are x values. Then we write a vertical segment, and we say x is between -6 and 7, and we have to say less than or equal to. Again, because the endpoints, their x values count. So if we were to read this out loud, we would say the set of all x values such that x is between -6 and 7, including -6 and 7. Or you can just say inclusive. So that's set notation. In interval notation, we say -6 to 7 with brackets, and the reason we use brackets instead of parentheses is because, again, the x values of the endpoints they're part of the domain. So that's it. That's the domain of the function. Now, what is the range of this function? Well, again, let's look at all these purple points here. What is the range of the function? The range is all of the possible y values of those points. So what are all the possible y values? Well, the y values are all real numbers. Again, imaginary numbers are not allowed to be outputs or inputs of functions. All real numbers between 1, 2, 3, between -3 and 2, because the y value of this point is 2 and the y value of this point is -3. So the graph doesn't go beyond that upper point or below that lower point. So that means that all these points, their y values have to be between -3 and 2. And we also have to say inclusive. Okay, and for set notation, we write the set of all the set of all y values, because now we're talking about y values. The set of all y values such that y is between -3 and 2, inclusive. And for interval notation, we write brackets again because we want to include the y values of the endpoints. So there you go. That is the domain and the range of that function in word form, set notation form, and interval notation form. So let's try another one. So here again we have a function represented by a graph, and we're going to find the domain and the range of the function given the graph. The domain is all of the possible x values of the points on that graph. And so again, if you look at the points on the graph, what are all the x values of the points on the graph? Well, the x values are all real numbers between 1 and 6. Now we don't have to say inclusive because we have hollow dots at the endpoints, which means that x cannot be equal to 1 and x cannot be equal to 6. 6 and 1 are not inputs of the function. They're not part of the domain. So we don't have to say inclusive. We just want all real numbers between 1 and 6. Those numbers are part of the domain. So in set notation, we say the set of all x values such that x is between 1 and 6, and we don't write less than or equal to symbols, just less than symbols. And in interval notation, we don't use brackets. We use parentheses. Brackets mean that 1 and 6 are part of the domain, but 1 and 6 are not part of the domain of the function, so we need to use parentheses. So that is the domain of the function written in 3 different ways. Now let's consider the range. The range of the function is all of the possible y values of the points on the graph. So look at all those purple points. What are all the possible y values? The y values of the points on the graph are they're the range of the graph. So the range is all real numbers, and you have to be careful here because in the previous problem we used the endpoints to determine the range of the function, but in this problem we're not going to really use this endpoint here. We're going to use this point because that point has the smallest y value. So all real numbers between, now let's look at the biggest or the point that has the biggest y value. That's this point here. That point has a y value that's equal to 4. And this point here, the lowest point, has a y value equal to 0. So we can say all real numbers between 0 and 4. Now this point is not really included. It's not part of the function. So the y value of that point doesn't really count. So 4 is not really in the range of the function. But down here, this point, its y value is part of the range. So we say 0 and 4, including 0. Okay, so not including 4, but including 0. In set notation, we say the set of all y values such that, and again we're using y values because this is range, the set of all y values such that y is between 0 and 4, but including 0. So we have to write a less than or equal to symbol next to the 0. whereas we only write a less than symbol next to the 4. And in interval notation, we use a bracket, and then a 0, and then a comma, and then a 4, and then a parenthesis. So again, that signifies that the range is all numbers between 0 and 4, including 0, but not including 4. So there's another example of a problem where we had to find the domain and the range of a function. So let's try another one. Here's an example where this graph is unbounded. It just keeps going. That's what this arrow means. Now, we don't know exactly what this graph does. It could go up and then come back down. But for this class, we're going to assume that the direction as it goes off the graph is continuing in that same trajectory. So if that's true, then the range is all real numbers, or excuse me, the domain is all real numbers greater than -4, because this point here has an x value that's equal to -4. And again, the domain is all of the x values, or it's the x values of all the points on the graph. But of course, this point doesn't really count because it's a hollow dot. So we say greater than -4, but not equal to -4. In set notation, we say the set of all x values such that x is greater than -4. And in interval notation, we use a parenthesis because -4 is not included in the domain. And then we use an infinity symbol, meaning it just keeps going. Any x value that's bigger than -4 can be, or it's in the domain. Okay, so now we want to look at all the points on the graph and understand that the y values of the points are the range of the function. So the range of the function is all real numbers greater than, and what is the smallest y value? And by the way, the reason that the x values could be anything bigger than -4 is because we're assuming that this graph just keeps going to the right. We're also assuming that this graph keeps going up. So the range is all real numbers greater than -3, because this point here has a y value that's equal to -3. In set notation, we say the set of all y values such that y is greater than -3. And in interval notation, we say -3 to infinity with parentheses. And by the way, whenever you have an infinity symbol, you always have a yellow parenthesis next to it, because there's no such thing as well, infinity is not an actual number, so nothing can ever be equal to infinity. Okay, so there you go. So that's another problem where we found the domain and range of a function. So it's important to understand that we're not only reviewing the domain and range of functions, we're also reviewing the different types of notation used to describe it. And we're going to use this notation throughout, again, the math curriculum, not just for the domain, but also for other things. So let's try another one. Now notice we have arrows on both sides indicating that the graph is going to the left and to the right and never stopping. So the domain is all real numbers. There's nothing that cannot be in the domain as long as the numbers are real, not imaginary. In set notation, we actually do not use the braces anymore. We just say all real numbers. And in interval notation, we say negative infinity to infinity. That's the interval. Okay. So for the range, notice that if this arrow keeps going in that direction, it's going to keep going down. And if this arrow keeps going in this direction, it's going to keep going up. So the range is exactly the same as the domain, all real numbers. Again, the range is all the y values of the points on the graph. So all real numbers. And interval notation, same as domain. Okay, so that was an example where the domain and the range could be any number as long as it's a real number. Okay, so let's try some more of these problems. You'll have a chance to do some of these on your own, but we're just doing these together now so you can remind yourself of what this stuff is and how it works. So now we have a kind of a break in the graph. Again, the domain is all the x values of the points on the graph. It's the x values of the points on the graph. So we're going to say all real numbers less than -3, or, it's very important that you say or and not and, or greater than 1. If you say and, that means that the x values are both less than -3 and greater than 1 at the same time. That's impossible. A number cannot be less than -3 and greater than 1 at the same time. So when you say or, you say one of these has to be true for a particular x value, but not both of them at the same time. So in set notation, we say the set of all x values such that x is less than -3 or x is greater than 1. And of course we get these numbers because the x value at the bound here is -3 and +1 there. In interval notation, we say negative infinity, that's this part here, comma, -3, that's this part here, and then we say union, the union symbol, and we pick up at 1, that's this part here, and then comma, infinity, that's this part here. So you can think of this union symbol as meaning or. It's kind of the equivalent of or in that sentence. So what about the range? Well, now we're just talking about the y values of the graph. So the y values are all real numbers less than 1 or greater than 4. So this point here has a y value of 1. This point has a y value of 4. And all of the points to the left of that point have y values that are less than 1. All the points to the right of this point have y values that are greater than 4. In set notation, we say the set of all y values such that y is less than 1 or y is greater than 4. And in interval notation, we say negative infinity to 1 union 4 to positive infinity. So again, we're just getting some review here. So let's do a few more of these problems before you try one on your own. I know you're probably excited to try one of these on your own, or you're ready to go, but let's do a few more problems before you try one on your own. So here we have, again, we're looking for domain. So what are all the x values of the points on the graph? The domain is the x values of the point on the graph, or all the points on the graph. So the domain is all real numbers except 4, because this point is hollow. So there is no 4. If you plug in 4, 1, 2, 3, 4 to your function, you don't get a y value. There's nothing there. And in set notation, we say the set of all x values such that x is not equal to 4. So when you say that that x is not equal to 4, that assumes that x can be everything else. Now, there are ways to describe this other than what you see here, but this is the way the mathematicians prefer, because it's just easier to write it that way. In interval notation, we say negative infinity to 4, parenthesis, union 4 to positive infinity with parentheses. Okay, so now what is the range? The only number in the range, again, the range is the y values of the function. The only number, or value, whatever you want to say it, the only value in the range is negative 2. In set notation, we say the set of all y values such that y is equal to negative 2. And in interval notation doesn't really correspond to this. Interval notation doesn't really make sense when it comes to this scenario, because interval notations are used for intervals, but this isn't really an interval. But if you had to write interval notation, it would look like this. So we're starting at negative 2 and ending at negative 2. Okay, so let's do another one. You can look at that if you want to go over that again. Okay, so what are all the x values of the points on the graph? So the x values are all real numbers except 2. Because if you plug in 2, you don't get, the graph is not there. It's a vertical asymptote. In set notation, we say the domain is the set of all x values such that x is not equal to 2. And in interval notation, we say the domain is negative infinity to 2 union 2 to positive infinity. Okay, and the range is all the y values of the points on the graph. All the possible y values of the points on the graph. So we say all real numbers, and that's it. We're assuming this graph continues to go down, and it looks like the graph actually goes through this horizontal asymptote, so all real numbers. That's the range. Whoops. That's the range of the function. So we say negative infinity to positive infinity. Okay, so we're just going to do one more of these before you try one on your own. So what is the domain? The domain is actually all real numbers. There's no real number that is not in the domain. It looks like we have holes, but you know, if this is a hole, then that means -3 is not in the domain, but actually -3 is in the domain, because when you count out -3, you have this point up here. And when you count out 1, 2, 3, 4, you don't have that point, but you have this point. So 4 is in the domain. So negative infinity to infinity. That was kind of a tricky problem. Now the range is the only values in the range. Remember, the range is all the possible y values of the points on the graph. The only values in the range are -1, 3, and 5. Because these points all have values, these points all have y values that are -1. These points all have y values that are 3, and this point has a y value that is 5. In set notation, we say the set of all y values such that y is equal to -1, or y is equal to 3, or y is equal to 5. You may see this written in a more compact form, but that's good enough for this class. Okay, so interval notation. This doesn't really apply. Interval notation is not really the best to use for this. But if you had to use interval notation, it would be brackets, -1, -1, union, bracket again, 3, 3, union again, bracket, 5, 5, and bracket. So there you go. Okay, so hopefully that jogged your mind. It jump-started your mind when it comes to domain and range of a function. If these pictures help you to visualize what domain and range are, you can take pictures of those. Get a picture of this problem set here, and a picture of these problems here. And you can use number 8 to help you do number 9. So we're going to find the domain of the function represented by this graph here. You want all of the possible, you want all the x values of the points on that graph. What are all the possible x values of the points on that graph? When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Now for the range, all right. So if you got that right, excellent. Okay, go ahead and try number 10. When you come back, we'll do it together. All right, we're back. So if you got that right, excellent. Okay, I want you to try number 11. And when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so I want you to take a picture of these problems here to help you with number 12. Go ahead and try number 12, and when you come back, we'll do it together. All right, we're back. So if you got that right, good. Go ahead and try number 13. And when you come back, we'll do it together. All right, we're back. Okay, so if you got that right, excellent. Go ahead and try number 14. Again, the purpose of this is to review interval notation and also to review the concept of domain. So try number 14. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, go ahead and try number 15. And when you come back, we'll do it together. Okay, we're back. So, if you got that one right, excellent. Okay, so let's do one more of these problems. Go ahead and try number 16. When you come back, we'll do it together. And by the way, you can take a picture of these problems if you'd like to use those to help you with number 16. When you come back, we'll do it together. Okay, we're back. So, if you got that right, excellent. Okay, so now we're going to find the domain of a function given the equation of the function. We're not going to worry about range at this point in the class. Domain is really more important when it comes to the overall math curriculum. Now remember, the domain of a function is all of the x values that you can plug into the function that will produce an output. So all of the inputs that you can plug in that will produce an output. But we know that a fraction with 0 as its denominator is undefined. So what that means is that x plus 2 cannot be 0. So you may recall from my intermediate algebra course that when you're trying to find the domain of a function given the equation of a function, it's often easier to think about what the x values cannot be rather than what they can be. So you can set up an inequality, or not an inequality, but I guess you could call it a false equation to help you determine what the domain is. And there we go. So you don't have to do this, but now we can say the domain of the function is all real numbers except -2. And in set notation, we say the set of all x values such that x is not equal to -2. This means that x can be any value other than -2. In interval notation, we write -infinity to -2 with parentheses, union -2 to positive infinity with parentheses. It's very important that you use parentheses next to the infinity symbols because brackets mean that infinity is equal to something, and infinity is not a number, so it can't be equal to something. It's also important that you use parentheses next to the -2 because, again, brackets tell us that -2 is in the domain, and that's the opposite of what we're trying to say. So, let's try another one of these problems. Here our function is the square root of x plus 5. Now again, when you're trying to find the domain of a function given the equation of a function, it's easier to think about what the x values cannot be. Again, the domain is all of the possible x values that you can plug in that will produce an output. But we know that the square root of a negative number is an imaginary. Remember, imaginary numbers cannot be inputs or outputs of functions. So what that means is that x plus 5 must be greater than or equal to 0. X plus 5 cannot be a negative number because then you have an imaginary output. Outputs are not allowed to be imaginary. So x plus 5 must be greater than or equal to 0. Again, you don't have to write this inequality, but it'll help you determine what the domain is going to be. So in order for this to be true, x must be greater than or equal to negative 5. So we just subtracted 5 from both sides. So that indicates what the domain is. The domain is all real numbers. Again, imaginary numbers are not allowed to be inputs of a function. The domain is all real numbers greater than or equal to negative 5. And in set notation, we say the domain is the set of all x values such that x is greater than or equal to negative 5. In interval notation, we write, and we're going to need brackets, or one bracket, a bracket, negative 5, comma, positive infinity with the parenthesis. So the bracket indicates that 5 or negative 5 is part of the domain, and again, you never write a bracket next to a infinity symbol. So there we have another example. Okay, on to the next problem. Again, when you're trying to find the domain of a function given the equation of a function, it's easier to think about what the x values cannot be rather than what they can be. The x values are the inputs of the function. We know both 0 and negative numbers produce an undefined logarithmic expression. So what that means is that 4 minus x over 2 must be greater than 0. Now again, you don't have to do this, but you can set up an inequality to help you determine the domain. I'm going to subtract 4 from both sides. And then I'm going to multiply both sides of the inequality by negative 2. Now, this is something that you need to recall from previous courses. When you multiply or divide both sides of an inequality by a negative number, you flip the inequality. Here it was greater than, but then it became less than. So we flip the inequality. Again, when you multiply or divide both sides of an inequality by a negative number, you have to flip the inequality symbol. So now we see what the domain is. The domain is all real numbers less than 8. And in set notation, we write negative infinity. Oops, that's interval notation. Set notation, we say the set of all x values such that x is less than 8. And in interval notation, we say negative infinity to 8. Now I want you to take a picture of problems 17 and 18. And I want you to use problem number 19 to help you attempt number 20. So again, we're looking for the domain of the function, all the x values that you can plug in that will produce an output. And remember, it's easier to think about what the x values cannot be rather than what they can be. So this explanation here will help you. So go ahead and try number 20, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, go ahead and try number 21. Remember, when you're trying to find the domain of a function, it's easier to think of what x cannot be, what the x values cannot be, rather than what they can be. So try number 21. When you come back, we'll do it together. Okay, we're back. There we go. So if you got that right, excellent. Okay, so I'm going to give you a chance to get a picture of numbers 17 and 18 again. And I want you to get a picture of numbers 19, 20, and 21. And I want you to try number 22. So go ahead and attempt number 22. Remember, when you're trying to find the domain of a function, it's easier to think about what the x values cannot be rather than what they can be. So try 22. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Okay, so now we're going to do the same types of problems, but we have an interesting situation here. This function has no square roots. It has no fractions. It has no logarithms. It has nothing that is going to restrict the domain. If you have 0 in the denominator of an equation, or if you have 0 in the denominator of a fraction, then it's undefined. There's no output for that corresponding input. If you have a negative number under a square root, then again, there's no output, because imaginary numbers are not outputs of functions. At least not in the curriculum that we're going to study, the parts of the curriculum. And so the domain is all the x values that will produce an output. But if you look at this equation, you can see that there's no x values that you can plug in there that are real numbers that do not produce an output. There's no problems. There's no logarithms where we can't have a negative or 0 in the logarithm. There's no fractions where we have 0 in the denominator, or square roots where we have negatives inside. So what that means is the domain is all real numbers. In set notation, we don't use braces, we just repeat what we said in words, all real numbers. It's just traditional for mathematicians to write that instead of set notation in this scenario. And in interval notation, we write negative infinity, comma, infinity with parentheses. So this is kind of a special situation. So here we have another example. Think of any x values that you could plug into this function that would not produce an output, or would have an undefined output. There is nothing. As long as you're plugging in real numbers, there's nothing that will cause a problem. So the function has no square roots, fractions, or logarithms that might restrict its domain. Therefore, x can be any number as long as it's a real number. Again, in this scenario, we just write all real numbers for set notation, and in interval notation, negative infinity to infinity. Okay, so now it's time for you to try a problem like that. Now, obviously the answer is going to be the same as these two answers. But I want you to think about why that is. I want you to look at this equation and think, why is it that the domain of this function is all real numbers? It may not be as easy as you think when it comes to this particular equation, but I want you to think about that. So go ahead and try number 25. It's pretty easy to understand why the domain is all real numbers for these functions, but for this one, students do tend to have to think a little bit. So try number 25. When you come back, we'll do it together. Okay, we're back. So if you plug in -3 for x, then you get 2 to the 0. Is this undefined? No. Exponent rule number 7 tells us that anything raised to the 0 power is 1. And if you want to look at the exponent rules, you can find those in my intermediate algebra course. So there is an output if our input is 0. Now, what if the exponent is negative? What if we plug in -5, for example? Then we get 2 to the -2 power. Is this undefined? No. Our exponent rules tell us that that's just going to be 1/4. This is exponent rule number 8. So there is an output for -5 as an input. Now, what if we have fraction powers? What if we plug in 1/2 for x? Is this undefined? Well, we get 2 to the 7/2, but that is the square root of 2 to the 7th power. Is this undefined? No. It's a real number. It's an output that we can define. So there actually are no x values that you can plug in that will produce an expression that is undefined. So we say that the domain of the function is all real numbers. Again, the domain of the function is all of the possible inputs that you can plug in that will produce an output. And in interval notation, we write -infinity to infinity. So there you go. Have you got that right? Excellent. Now here we have another example. This is an easier example. But I want you to think about why the domain is all real numbers. So try that problem, and when you come back, we'll do it together. All right, we're back. So have you got that right? Excellent. Okay, so we reviewed the domain and range of a function, and now we're going to go on to another topic called differentiability. But before we go on to that topic, we're going to review the definition of the derivative. Now, if you forgot the logic behind this, if you're a little rusty on this, or you just completely forgot, that's okay. It's not really that important that you understand this right now. But we're just going to quickly go over this. So remember, if you want to find the instantaneous rate of change of a function at some point, that is the slope of the tangent line at that point, the slope of the line that is tangent to the graph at that point. So the slope of that blue line is the instantaneous rate of change of the function at this purple point. Now, when we say instantaneous rate of change, we mean how fast the y values are changing as the x values are changing. But how do we find the slope? Well, what we do is we we mark another point on the graph, and we find the average rate of change, which is the slope of the green secant line. So we figure out the slope of the green secant line, and then we bring this point closer and closer and closer, and we continue to calculate the slope of the green secant line. So the green secant line is going to, its slope is going to change as we get closer and closer. Whoops, I gotta go through the right points there. So the slope of that line is going to change as the point gets closer and closer to the purple point. So we're getting closer and closer and closer, and we keep calculating the slope of the green line, and the slope of the green line keeps getting closer and closer and closer to the slope of the blue line, which is what we're really looking for. That's the instantaneous rate of change. The slope of the green line is only the average rate of change. So what we do is we find the value that the slope of the green line is approaching, and that value is the slope of the blue line, the slope of the line that is tangent to the graph at this purple point. So you don't have to think about all of the technical details and notation right now, but this demonstrates what's happening, what I just showed basically. And the slope of the green line is this expression here. Remember, we use function notation, and going from here to here is very difficult for students, very difficult. If you don't have a complete understanding of that, you can look at this and review if you want to, but again, this is not really that important in this class today. If you simplify the slope of the green secant line, you get this expression, which is called the difference quotient. But if you find the limit of that expression as h approaches 0, that's actually the slope of the tangent line, the slope of the blue line that I was describing above. And that is the definition of the derivative. That's the instantaneous rate of change of a function at some x value. That's the slope of the blue line that is tangent to the graph at the special point that we're referring to. So that's some review there on the definition of the derivative. We also need to review continuity. Remember, a function is continuous if there are no breaks in the graph. You see these breaks here that I'm highlighting in blue? Those are parts of the graph that are not continuous. We have a discontinuity. So this is called a removable discontinuity, this is a jump discontinuity, and this is an infinite discontinuity. Now here is the algebraic definition of a continuity, but we don't really need to go into that now. So now we are going to learn this new term. Again, we learned about continuity. That's when a function doesn't have any breaks in the curve. That's these situations here. We learned about continuity when we don't have any of these blue breaks in the graph of the function. But now we're going to learn something called differentiability. Differentiability is simply the ability to find a value for the derivative at some x value. A function is differentiable at x equals some value if f prime of a exists. So all that means is that if the derivative can be found at some x value, then the function is differentiable at that point. So let's say that we have some function, and it turns out that the derivative of the function is equal to, say, 1 over x. Well, if we plug in 0 for x, the derivative is not defined. So we say that the function is not differentiable when x is equal to 0. So that's an example of where a function is not differentiable. So we need to explore all these scenarios where a function is not differentiable. It turns out that a function is not differentiable wherever you have a discontinuity. So we looked at these discontinuities on the previous page. In this first graph at the left where x equals 1, we have a discontinuity, right? So the function is not differentiable there. We can't find the derivative. And at x equals -2, this function is, well, it has a discontinuity, so we can't find the derivative of the function there. And here we have a discontinuity, so we can't find the derivative when x equals -2 here either. So it's very important to remember that if a function is discontinuous at x equals some value, then it is not differentiable at that value, at that x value. Now, you would take some in-depth explanation to explain exactly why that is. In these two scenarios, the function is not even defined at that discontinuity. If you plug in some x value, you don't get an output. The derivative, as we explained previously, is defined by this expression. But you cannot possibly find the value of this limit if this value doesn't even exist. There's nothing even to plug in to the expression. So that's why a function is not differentiable. You can't find the derivative where you have a discontinuity. Now, in this situation, it's a little bit different. In this situation, it turns out that that limit does exist if h is approaching 0 from the left. But the limit does not exist if h is approaching 0 from the right. Now, we're not talking about what x is approaching. We're talking about what h is approaching. So I know that's kind of confusing, but the reason that the limit doesn't exist is because you have 2 points, and one of the points has to be here. This is f of x down here. And your secant line is here, so as this point gets closer and closer, this tangent line actually becomes, well, it gets closer and closer to a vertical line, but a vertical line doesn't have a defined, slope. So the left limit exists, but the right limit doesn't. Now, why do we care about that? Well, remember, in order for a limit to exist, first of all, we call this a two-sided limit because h does not, or the 0 does not have a purple plus. It does not have a purple plus or a purple negative symbol. So this is a two-sided limit. In order for the two-sided limit to exist, the left limit and the right limit both have to exist, and they have to be equal to each other. But one of the limits doesn't actually exist. So these are just some brief explanations for why a function is not differentiable at a discontinuity. Now, you might wonder, well, what about when a dot is above or below a removable discontinuity? Does the limit exist there? Well, no, it doesn't, for the same reason that it doesn't exist here, or a similar reason that it doesn't exist there. So I know that this is pretty complicated, but again, you don't have to know these specifics. All you have to know is the general idea. If a function is discontinuous at some x value, then it is not differentiable at that x value, meaning you can't find the derivative. But we have other scenarios where a function is not differentiable. Functions are not differentiable where we have discontinuities, but they're also not differentiable when the graphs of the functions have sharp turns, or where the graph of a function has a vertical tangent line. So what in the world does this mean? Well, first of all, notice that there are no discontinuities here. We have a sharp turn here, but that doesn't mean that the function is not continuous there. It's continuous. There's no breaks in the graph. But because we have this sharp turn and a sharp turn here, we actually cannot find the value of the derivative. There is no value for the derivative when x is equal to -2 in this example. We're going to demonstrate later on using algebra that it's not possible to find the value of the derivative when x is -2 in this example. But for now, let's think about the geometric interpretation. So let's say we're going to try to find the slope of the line that is tangent to the red graph at this point here. Well, we can draw a tangent line like this, but we can also draw a tangent line like this, or like this. There's actually an infinite number of ways that we can draw a line that is tangent to the graph at that point. So the tangent line is not really clearly defined. So that's why the derivative actually does not exist at that point. I know that's kind of weird to think about. Same is true down here. We can draw a line that's tangent to the graph at that point there. We can also draw a tangent line there, or a tangent line here, or a tangent line here. There's just an infinite number of tangent lines that we can draw. So what is the instantaneous rate of change of the function when x is equal to 0? Well, there is no clearly defined rate of change, and you can actually show that algebraically also. Although we're not going to do that today because we don't want to get bogged down with that stuff. You're not really required to know that for the most part in the calculus curriculum. So we have another scenario where the derivative is not defined. Again, notice that we don't have any discontinuities, so there's no problem with discontinuities, but at this point here, I know it's kind of hard to see, but at this point here, the line that is tangent to that graph is actually vertical. So remember, when you're finding the derivative, the whole point is to find the slope of the line that is tangent to the graph at that point. But recall that a vertical tangent line doesn't have a slope. So the derivative doesn't exist at that point. We say that the function is not differentiable at that blue point. So those are the geometric reasons that a function is not differentiable when you have a sharp turn or a vertical tangent line. So again, I know that this stuff is kind of complicated, but there's only two things that you really need to know based on what we just talked about, and that is, if a function is discontinuous at x equals a, then it is not differentiable at x equals a. If a function is discontinuous at some x value, you can't find the derivative at that x value. You also need to know if a function is continuous on an interval. If the function is continuous on an interval, like these graphs are all continuous, then it is differentiable on this interval, except at x values where its graph has sharp turns or vertical tangent lines. Okay, now there's one other thing that we need to talk about before we move on. This is a very important theorem when it comes to calculus, and really it's more important for the advanced placement calculus AB exam. You're going to be expected to know this. If a function is differentiable at x equals a, if you're able to find the derivative at some x value, then that proves that the function is continuous at that x value. That's a very, very important theorem. You're going to be told on the Advanced Placement Calculus AB exam that a function is differentiable, and you're going to be expected to conclude from that that it's continuous. And we're talking about differentiability on intervals. You're going to be told it's differentiable on some interval, and you're going to be expected to conclude from that that it's also continuous. So this is an important theorem. Now, it's not true that if a function is continuous, that then proves that it's differentiable. That's not correct. We just showed that. These functions are all continuous pretty much everywhere, but they're not differentiable. So if a function is continuous, that doesn't mean that it's differentiable at some x value. But if we know that a function is differentiable on some interval or some x value, then that actually does prove that it is continuous. So I know that these things are kind of confusing to think about, but this is going to be important when it comes to the concepts that you're going to use when taking the advanced placement exam, and also some problems possibly in this curriculum. So now we're going to get some practice with these concepts. We're asked to write all the x values where there is a discontinuity, and then we're asked to write all x values where the function is not differentiable, where you cannot find the derivative. So let's look at this green graph here. Obviously we have a discontinuity when x is equal to -2. There's a hole there, right? But that's the only discontinuity. And we're also asked to find where the function is not differentiable. Now, functions are not differentiable where you have a sharp turn on the graph of the function, and that's at -4. Remember that functions are not differentiable where you have a discontinuity. So we know we have a discontinuity at x equals -2, right? So you can't find the derivative when you have a discontinuity. But here, it's kind of hard to see, but here, the graph is actually, there's one point where the tangent line is actually vertical. So we're going to say at x equals 1, the function is not differentiable. Now, to be honest with you, that's kind of hard to see. It'd be hard to prove that without actually doing the algebra, but for these problems, we're just going to assume that the tangent line at this red point is vertical, the line tangent to the graph. Okay, so let's look at this blue graph. Where are all the discontinuities? Well, we have a discontinuity at x equals 1. That's a jump discontinuity. Again, this is called a removable discontinuity. And we also have an infinite discontinuity at x equals 3. That's a vertical asymptote. Now remember, if a function is not continuous at some x value, that means it's not differentiable. So the function is not differentiable at x equals 1. It's also not differentiable at x equals 3 because, again, we have a discontinuity. Now this, it's a little hard to see, but that's a sharp turn. So at x equals 5, the function is not differentiable either. So again, it's so important to remember. A function is not differentiable at discontinuities, but it's also not differentiable when you have a sharp turn. So let's go to this purple graph. Where are the discontinuities? Well, we have a discontinuity at x equals 2, and I think that's the only one. That's a removable discontinuity. Where do we have x values, or what x values do we have where the function is not differentiable? Well, obviously x equals -2 because we have a sharp turn. We also have a sharp turn here at x equals -1. And of course, the function is not differentiable when it's discontinuous. All right. So let's go down to these problems. First, we're going to find where the function is discontinuous. Obviously, at x equals -4 and at x equals -2. And where are we not able to find the derivative? Well, we're not able to find the derivative at discontinuities. So obviously x equals -4 and x equals -2. And I don't see any sharp turns or vertical tangent lines, so you don't have to worry about that. So let's go to the red graph here. Do we have any discontinuities? And the answer is no, we don't. There's no breaks in the graph, so no discontinuities. Do we have any areas or any x values where the function is not differentiable? We do have a sharp turn when x is 0, and we do have a vertical tangent line when x is equal to 3. Right here, the tangent line is vertical. So, I want you to get a picture of, you don't really need a picture of this information at the right, but you can if you want to. I definitely want you to get a picture of these two pages, and I want you to try number 32. Use problems 27 through 31 to help you. Try number 32, and when you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. Go ahead and try number 33. And when you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. Go ahead and try number 34. When you come back, we'll do it together. All right, we're back. So if you got that right, excellent. Go ahead and try number 35, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Try number 36, and when you come back, we'll do it together. All right, we're back. So if you got that right, excellent. So again, we're reviewing continuity, and we're also learning this term differentiability. But now we're going to find the algebraic reasons that we can't find the value of the derivative at certain x values. Now, we showed a graph of this function when we explained why the derivative is not defined at sharp turns. But now we actually have the equation of that graph. And we're going to explain algebraically why we cannot find the derivative, because you're probably wondering, what exactly happens when you use your definition of the derivative. Remember, all of the information that we learned about how to find the derivative is based on that definition of the derivative that you see here. We just found easier ways to come up with the value of this limit. So all that information that you learned from previous classes is going to be important here. We're going to use all the differentiation formulas that we learned, and we're going to go ahead and find the derivative. So the derivative of a constant is 0, and the derivative of a constant multiplied by a function is just the constant times the derivative of that expression. But we don't have to write that. The derivative of this is 2/3 times x plus 2 to the 2/3 minus 1 power. So we use the power rule. But we have a function inside another function. So what that means is we do have to consider the chain rule. We found the derivative of the outside function and we kept the inside function, and now we're going to multiply by the derivative of the blue inside function. So we have to multiply by the derivative of x plus 2. But of course the derivative of x plus 2 is just 1. So we have negative 2/3 times x plus 2 to the negative 1/3 power times 1. So I just want to make it clear that that turned into 1 there. Okay, but we don't really know what this expression means. We don't really know what this means at all, because we have a negative exponent and a fraction exponent. That doesn't really have any direct meaning. So we're going to get rid of the negative exponent, or we're going to convert it to a positive exponent. So we have the following expression now. That was using exponent rule number 8. Again, you can go to my intermediate algebra course if you want to review the exponent rules. But we still don't really know what this expression means because we have a fraction exponent. So we have to translate it to the cube root of x plus 2. Now we can figure out what this actually means. But I want you to notice something very important. First of all, what are we doing with these problems? Well, it tells us to determine algebraically that each function below is not differentiable at the indicated x value, x equals negative 2. So remember, at x equals negative 2, we have a sharp turn. So for some reason, we cannot find the derivative at x equals negative 2. This pink value here. Why is that? Well, let's look at the formula that we came up with for the derivative. This formula gives you the slope of the line that is tangent to the graph at whatever x value you want to plug in. But if you plug in negative 2, look what happens in the denominator. If you plug in negative 2, you get, well, let's write it over here. F of negative 2 is equal to negative 2 over 3 times the cube root of negative 2 plus 2. But we have a problem. We have the cube root of 0. Now, what is the cube root of 0? What number times itself and then times itself again is equal to 0? Well, obviously, that's just 0. So we have negative 2 over 3 times 0. 3 times 0 is 0. And this is an undefined expression. So how in the world can you possibly find the value of the derivative if you plug in an x value and you get this expression? The answer is you cannot find the value of the derivative. And we explain geometrically why that's true. If you try to draw a line that's tangent to the graph at that point, there is no defined tangent line. Or maybe one way to think about it is you can come up with an infinite number of tangent lines. So it makes sense geometrically that there would be no derivative there. So that explains why the function is not differentiable at that x value. So we can conclude by saying f prime of negative 2 does not, well, we can just say f prime of negative 2 is undefined. That's probably good enough. All right? So this shows you algebraically why the function's not differentiable there. Now here we have another example. At this point here we have a vertical tangent line, and we have the equation of that graph. And so let's explain algebraically why we cannot find the value of the derivative at x equals 3. Now, it's a lot easier to find the derivative when we change these expressions to x minus 3 to the 3/5 power and x minus 3 to the 8/5 power. Now we can find the derivative, and we're just going to use all of our differentiation formulas. And of course the derivative of a constant is 0. And by the way, we'd have to use the chain rule here. I don't know if I have enough room to demonstrate that, but just to be thorough, technically we would have to use the chain rule, so we'd have to multiply by the derivative of x minus 3. But the derivative of x minus 3 is just 1, so we don't really need to write that. And let's see if we can make some more room here. We'd have to use the chain rule over here. So we have to multiply by the derivative of x minus 3. So when you find the derivative, you don't have to write all this stuff. It just takes forever to write every single thing. You can just do this quickly in your head. I'm just being thorough for educational purposes. The derivative of that is 1, and we have 8/5 times x minus 3 to the 3/5 power times 1. And so now we're left with an expression, but we don't really know what it means. So in order to actually figure out what this means, we have to use exponent rule number 8 and get rid of that negative on the exponent. And we can also use exponent rule number 10 to change this to the 5th root of x minus 3 to the 3rd power. And we're going to do the same thing for the other root. We have 6 over 5 times the 5th root of x minus 3 squared. So now we can see what's actually happening. Alright. So now we need to explain why the derivative doesn't exist when x is equal to 3. Well, it's pretty obvious, right? When you plug in 3, what happens down here? You have 0 in the denominator. If you have 0 in the denominator, the function doesn't have a defined output. So if the derivative function doesn't have a defined output, that means that the original function, f of x, is not differentiable when x is equal to 3. So f prime of 3 is undefined. Okay, so let's go to another problem. Again, we need to demonstrate that this function is not differentiable at x equals 4, and we need to do this algebraically. We can see geometrically why it's not differentiable. In order for a function to be differentiable at some x value, the function has to be defined at that x value, but you can see here that the graph is not even there. There is no output if 4 is your input. But we need to demonstrate algebraically, so we're going to find the derivative of this function using the differentiation formulas. Now there's two different ways to do this. One way, in fact the way that students typically prefer, is to change x minus 4 to x minus 4 to the first power. And I have not demonstrated this yet, but now is as good a time as any to show you some different ways to find the derivative. We're then going to use exponent rule number 8 to raise that up. So we change the form from this to this, and then you can find the derivative using the chain rule. The other way to do it is to go ahead and just take the derivative, or find the derivative immediately, and that method requires the quotient rule. So let me move this down because we're going to need a lot of room to demonstrate both of these options. I'll call this option 2. But for now, let's just use the quotient rule. I'll show you both methods. Again, we have not demonstrated the second option, but we'll call this the first option where we use the quotient rule. Sorry. So the derivative is, remember, when you find the derivative of a fraction, you multiply the derivative of the numerator by the denominator, and you subtract the numerator times the derivative of the denominator, and all that must be divided by the denominator squared. That's the quotient rule. And so the derivative of 1 is 0. And by the way, you don't have to show the d over dx's when you do this. You can just do it quickly in your head if you feel comfortable doing that. So this became that, just to be clear, that became that, and that's all over x minus 4 squared. So we have negative 1 over x minus 4 squared. So using this expression that we found using the differentiation formulas, we can demonstrate algebraically why the function is not differentiable. Remember, differentiability is the ability to find a value for the derivative at some x value. But if we plug in 4, you can see that the derivative is undefined. So you would expect something to happen there. So we can conclude f prime of 4 is undefined. We showed algebraically why that is. Now, it doesn't look like we have much room to show the second option, but if you use the chain rule, you can use that second option there. We'll demonstrate that maybe in another problem, but at least you have the setup there. Okay, so I want you to get a picture of these two problems here. and a picture of, well, you can use number 39 to help you with number 40. So you can see that we have a sharp turn here, which means that the function is not going to be differentiable at x equals 0. And so that's the geometric explanation of why we can't find the derivative. We have a sharp turn, but let's explain algebraically. Now, when you find the derivative of this expression, it's easier to change that expression to x to the 2/9 power using exponent rule number 10, so be aware of that. So find the derivative and then explain why when you plug in 0 you get an undefined expression for the derivative. So try number 40. When you come back, we'll do it together. Okay, we're back. So if you got that right, good. So we're just explaining why some functions are not differentiable at certain x values, why you cannot find the derivative of a function at certain x values. So over here we have a vertical tangent line at x equals -1. So I want you to find the derivative of this function using the differentiation formulas, and then explain why when you plug in -1 into that derivative formula, you get an undefined expression. Therefore, the function is not differentiable at that x value. Try number 41. When you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and take a picture of these problems. And I want you to try one more of these. So we can see geometrically that the function is not differentiable because the function is not even continuous at x equals -1. There's no tangent line. There's no line that's tangent to the graph of the function because there is no graph at x equals -1. It's an infinite discontinuity. So try number 42. You're going to have to use either the quotient rule or that other option they were talking about previously. So find the derivative of this function and then show that the derivative is undefined when x equals -1. When you come back, we'll do it together. Okay, we're back. So we demonstrated algebraically that the function is not differentiable when x is equal to -1. So we talked about these situations earlier in the class. When you have a jump discontinuity, a function is not differentiable at that discontinuity. Now, a jump discontinuity would look like this if we were to write the equations out. So it's actually a piecewise function. And if we want to demonstrate algebraically why the function is not differentiable, I'm just going to briefly explain to you how that would be done. You're not required to do this. Is that clear? You're not required to do this. So I'm just demonstrating, just if you're curious to know how this would be done. So we can't use the differentiation formulas directly. We have to use the definition of the derivative. So we mentioned earlier that this is the definition of the derivative. Now notice that the derivative is a two-sided limit. Remember, if you have a one-sided limit, then you would have either a blue plus sign or a blue negative sign down there. The blue negative sign means the left limit, the limit coming from the left, and the plus sign means the limit coming from the right. In order for this two-sided limit to exist, the left limit and the right limit must exist, and they must be equal to each other. Well, it turns out that the left limit doesn't even exist. The right limit does exist, but the left limit does not. So if the left limit doesn't exist, then immediately we know that it's just the function's not differentiable. This derivative doesn't even exist because the limit doesn't exist. Remember, a derivative is a limit. So that's the situation where we have a jump discontinuity. We talked about the situations where we have infinite discontinuities. A removable discontinuity would give us well, we'd have an undefined output, so f of x wouldn't even exist in that case. We talked about that, so that's we don't really need to demonstrate that algebraically. But here we have a sharp turn. How would you demonstrate algebraically that the derivative doesn't exist, meaning the function is not differentiable at x equals 0? Well, again, we'd use the definition of the derivative. And in this case, it turns out that the left limit and the right limit, they both exist. So in the previous problem, one of the limits actually didn't exist, but in this problem, they both exist, but the problem is they're not equal to each other. The left and the right limits must be equal to each other in order for the two-sided limit, which is the derivative, to exist. So that's why this function is not differentiable at x equals 0. In these situations, you can't just demonstrate algebraically like we did in the previous problems. You have to go into the definition of the derivative and explain in more detail. But again, don't be afraid by this because you're not really required to do this in the calculus curriculum. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1. And you get a picture of these analogies if you want to use those to help understand what the domain and range are. Here's screenshot number 2 and number 3 and number 4 and number 5 and number 6, number 7, and number 8, and number 9, and number 10, and 11, 12, and 13. But don't go before you get your homework. Let's look at the homework. Here's a screenshot number 1 of the homework. And screenshot number 2. And number 3. 4. 5. And 6. But don't go before you get the answers to the homework. Remember, it's not enough just to attempt the homework, it must be done correctly. So here's screenshot number 1 of the answers to the homework. And screenshot number 2. And number 3. And number 4. So remember, if you don't do the homework, it's 100% guarantee you're going to learn absolutely nothing in this entire course. So get that homework done, and I'll look forward to seeing you in the next class.